In this problem, we are asked to find the maximum number of equivalence relations on a set with 3 elements. Now here I've just called the set as A with the elements A, B and C. Okay. Now the thing to understand is that every relation is a subset of A cross A. Okay. Or subset of A cross A. Okay. And how many elements can at most be in R? Well, A has 3 elements, so the number of elements in A cross A is 9. So at most 9 elements can be in R. But that is not the question. The question is not find the maximum number of elements in an equivalence relation. Okay? The question is, what is the maximum number of equivalence relations? Okay? Now, the set which contains all the 9 elements will clearly be an equivalence relation, because all the conditions have to be satisfied. No violation can happen, because if AB is there, BC is there, AC should be there, because everything will be there in the in this universal relation where all the pairings are part of the relation. So this is clearly one equivalence relation, but that's not the only one. There could be many others. So how many? That is the question. So let's start with the simplest equivalence relation with as few elements as possible. Okay. Now we already know that in order to have an equivalence relation, it should be reflexive, symmetric and transitive. Okay. Reflexive means AA, BB, CC must be part of all the relations. So the minimum you can have is AA, BB, CC. So let's call this as set R1. This is the smallest set and still satisfying equivalence condition. Okay. Now what can we do to get another relation? Let's add something extra. Let's see if we can add one element. So we have AA, BB, CC. Let's say we add AB. The problem is if you add AB, then you have to definitely add BA also, because it needs to be symmetric. Okay, but can we stop here? Can we not add anything else and still not violate any condition? Well, yes, because AB, BA means that symmetric condition is not violated and no other extra element is there to violate transitive. Okay, therefore this is a symmetric equivalence relation. Now you can see that we had choices. Instead of AB, we could have done BC or we could have also done AC. BC means CB would have been there. AC means CA would have been there. The other things are obviously there. The base condition is necessarily should be satisfied. So we have R2, R3 and R4. Okay. Now the question is, well, we also know that we can build another thing with 9 elements which will be an equivalence relation. But is there something in between? For example, this has 3, this has 5. Maybe we will have another set with 7 elements that can be an equivalence relation. Let's see. So now we have AA, BB, CC and let's say AB and BA. Can we add just BC to this? Okay. Now one problem is, well, this is 3 plus 3, 6. But we know that if we add BC, CB will get added automatically. Okay. But is that enough? If we just have this, is it an equivalence? Well, it meets the condition for symmetric, but does it meet the condition for transitive? Because AB and BC are there, that means AC should be there. Okay. Okay, let's add that. But because AC is there, CA must also be there. Now this means 1, 2, 3, 4, 5, 6, 7, 8, 9. All the elements have been added, nothing more to add. That means this is the last equivalence relation that we can get. So we cannot get something with 6 or 7 or 8 elements. The only possibilities are 3 or 5 elements or 9 elements. But with 5 elements you have 3 different relations. These relations have the same number of elements, but they are different relations because their elements are different. The sets themselves are different. So the final answer is we can have at most 5 different equivalence relations on the set A is equal to ABC.